Okay, so we'll start. Yeah, good evening, everybody. Very happy to have Latham back with us on this OSMU lecture series. This is our fourth lecture of the year. So happy to introduce Latham briefly. He's currently a faculty at the Higgs Center for Theoretical Physics of the University of Edinburgh. He moved there a few years ago, and before that, Latham was a faculty at the Perimeter Institute. He obtained his PhD from Princeton University in 2006 and was then a postdoc fellow at the Canadian Institute for Theoretical Astrophysics in Toronto before he joined Perimeter. Latham has very wide-ranging research interests in cosmology, particle physics, gravitational waves, black holes, and mathematical physics. Yesterday, I was looking up his papers on InspireHep. It's very impressive, the diversity of subjects on which he has worked on and made contributions. Latham has been also deeply interested in understanding where the unexplained structures and patterns in the standard model of particle physics come from. An important work in this regard is his paper titled The Standard Model, Exceptional Jordan Algebra and Triality. His other noteworthy works include Probe of the Early Universe with Inflationary Gravitational Waves with Paul Steinhardt and Non-Associative Geometry, Spectral Action Principle at Particle Physics with Shane Farnsworth, and several other very interesting papers. Latham has also been very interested in self-similar quasi-periodic tilings, like the Penrose tiling, both because of their mathematical beauty and because of their connections to physics, for example, as a new tool for discretizing scale-invariant physical systems. This is what Latham talked in OSMU last time. In 2018, along with Neil Turok and collaborators, Latham proposed a new cosmological model, the CPT-symmetric universe, in which the universe before the bang is the CPT mirror image of the universe after the bang. And more recently, in a fascinating work, they have generalized this idea to a CPT-symmetric black hole, now called a black mirror. And this is what Latham will tell us about today. Pleasure to have you with us. Please, over to you.
All right, thank you for the very kind introduction, Tejinder, and for the invitation. So I wanted to tell you about our recent paper from December. Here's the archive number if you're interested, which I should say this is a paper written in collaboration with Neil Turek over here and Kostas Sanavaris, an outstanding PhD student here in Edinburgh, and I want to emphasize really his leading role in the whole project. And so the question is, we know that in general relativity, when a object undergoes gravitational collapse, that an event horizon forms. And the question is, what is on the other side of that event horizon? The conventional picture for decades now is that the event horizon connects our exterior spacetime to an interior spacetime that contains a singularity, and perhaps more than that. In this paper, we describe a topologically distinct solution where the event horizon connects our exterior to a CPT mirror image exterior, and so that it has no interior, no curvature singularities. We think it's interesting because it's, first of all, I'll try to explain how it seems to naturally arise in in the CPT-symmetric picture of cosmology that we have been interested in recent years, and are increasingly excited about, and also how it the standard picture of black holes with an interior has a number of nagging problems and puzzles associated with it that people have, in some sense, gotten used to, but that are still there and that we think are neatly resolved in this picture. So I'll try to explain all of that. Okay, so let me just dive in. So a little bit of historical background. So as you all know, the first non-trivial exact solution of Einstein's equations was given by Schwarzschild in 1916, right before he unfortunately died in the trenches of World War I. And it describes the space-time around a massive, static, spherically symmetric, non-rotating object. So here's the line element, where here f is this function 1 minus 2m over r, and d squared omega, as usual, is the line element on a round 2 sphere. So in modern terms, nowadays, people have gotten used to the idea of thinking about the maximal analytic extension of this space-time, the so-called Kruskal extension, and drawing its Penrose diagram. So I've drawn the, now this is breaking with historical order here, but just to put everything in context, I've drawn the full conventional analytic extension of the Schwarzschild black hole, and you see it has 4 parts. It has 2 exteriors, which I've labeled I and I prime here, 1 and 1 prime, and then there's also 2 interiors, 2 and 2 prime. In those terms, this metric only describes one of the exteriors, the blue diamond that I've shown here. So this blue diamond on the right-hand side, because in these original Schwarzschild coordinates, these coordinates with t and r, time goes to plus infinity as you reach the black hole horizon here. So the coordinates just don't make it to the horizon, let alone inside the horizon. Okay, so what to make of it? Well, Einstein did not like the interior. He thought it didn't. He thought it wasn't real. He thought that because of this issue that it seems to take an infinite amount of time to that you don't see things cross the horizon. That the horizon seems to lop off a region of space that is unobservable to you, and also that if you did take the interior seriously, the region r less than the horizon radius 2m, that the metric seemed to have a singularity in there. So in an attempt to get around those problems and see how to make sense of this space-time without the interior, Einstein and Rosen wrote this 1935 paper, which introduced what we would now call the Einstein-Rosen bridge or Einstein-Rosen wormhole. The idea was we start with the previous solution of Schwarzschild, but in GR we're free to choose work in different coordinates that may then end up covering bigger or smaller patches of the space-time. And their idea was, let's switch from Schwarzschild's coordinate r to this new coordinate sigma, defined as follows. So in terms of that, the line element in terms of sigma looks as follows. But now, sigma positive covers the previous blue diamond. It's just the same as the Schwarzschild metric, but in the previous blue diamond. But if we now allow sigma to become negative, it also covers the pink diamond on the left, the other exterior from the modern viewpoint, but still never goes inside the horizon. So we just let t run from minus infinity to infinity, sigma run from minus infinity to infinity. And we cover these 2 exterior diamonds. And they thought, because all the coordinates were now running from minus infinity to infinity, that they were describing a complete space-time, and they thought they had found a solution for how to get rid of the interior of the black hole and make sense of the Schwarzschild space-time. Okay, now so what happened to that solution? Well, a couple of arguments subsequently came along, which convinced most people that the interior really was there. So So first there was this paper, an important paper by Oppenheimer and Snyder in 1939, where they gave a solution describing the collapsing that was supposed to describe an idealized form of the collapsing matter of a star collapsing under its undergoing gravitational collapse, and in particular argued that the matter continued to collapse in this solution even across to radii smaller than the horizon at 2m. And eventually formed a singularity at r equals 0. And here is a sort of picture of that collapse drawn actually not from this paper, but from Penrose's famous paper in the 60s proving the singularity theorem, that if this picture of gravitational collapse that Oppenheimer and Snyder outline is correct, that there is indeed a singularity that forms at the center of the interior of the black hole. That it's not just an artifact of the spherical symmetry of the Schwarzschild solution. Okay, and then a second thing that happened, another important ingredient that convinced people that the horizon was not the end of the space-time, was that they realized that, okay, although the original Schwarzschild coordinates r and t, or the Einstein-Rosen coordinates sigma and t, didn't cover the interior, that you could switch to different coordinates that did. And so these are the simplest and first coordinate transformation of this form is to switch to the so-called Eddington-Finkelstein coordinates, although my understanding, and people can correct me if I'm wrong, but my understanding is that actually this was first written down, apparently in print, in a paper by Penrose in the 60s, and that he attributes it to Eddington and Finkelstein, which maybe he heard about it from them. I don't know. But anyway, so the change of coordinates is that we switch from Schwarzschild's original coordinates t and r. We replaced the time coordinate t by a new null coordinate v. So this coordinate remains non-singular along the horizon and allows you to sort of measure time as you go up and down the horizon in a non-singular fashion, as opposed to the Schwarzschild time, which becomes t is just infinity everywhere along the black hole horizon. And so again, expressed in terms of the modern Kruskal extension, this new coordinate system. Oh, by the way, I should notice that there's a plus or minus subscript on v here. That's because there's actually two different coordinates you can choose. If you choose the plus subscript and you choose the plus sign everywhere there's an option, the top sign, those are the so-called ingoing Eddington-Finkelstein coordinates, and those cover this region that I've shown here. They cover the black hole horizon and the exterior, and then they extend to the black hole horizon and inside to the upper interior. So they cover this blue region. Alternatively, if we took the minus sign, those would be the so-called outgoing Eddington-Finkelstein coordinates, which I haven't shown because they cover instead the white hole horizon. So they would cover this region here, the exterior and the white hole horizon and the interior to the past of the white hole horizon. Okay, so those two arguments, the Oppenheimer-Snyder argument and the sort of physical Oppenheimer-Snyder argument that matter seems to continue to infall with nothing in particular seeming to obstruct it, and the fact that you can make a coordinate change that reveals the quote-unquote singularity at the horizon to be a mere coordinate singularity, basically convinced everybody that the interior was real and that the black hole horizon was just the connecting membrane between the exterior labeled 1 here and the interior labeled 2. Okay, but, you know, as I mentioned, there are reasons to be suspicious of this interpretation. It may be right, but let's just review some of the reasons to wonder about that. Okay, so first of all, the first two reasons here are sort of the original reasons that Einstein wondered about it. was skeptical. So one is that, you have this region of space-time, the interior, that seems hidden from observations. No, not even light signals can escape from it to be detected by an exterior observer, classically. So you might wonder, well, if the laws of physics are telling us that something is hidden from us, even in principle, hidden from observation, it's unobservable. Is it really there? Famously, something similar happens in quantum mechanics, and the modern view is that the things that are in principle unobservable in quantum mechanics are really unobservable. They're really not. They're really sort of not a part of physical reality. We learn to trust what the laws of physics were telling us there, even if it was kind of counterintuitive. Um, and then the other thing is that, again, as Penrose showed quite generically, if the interior does exist, then there's a very violent singularity, a curvature singularity, in there where the laws of general relativity break down, and there's no way to naturally extend beyond that singularity. Um, uh, Now, beyond that, since in more modern times, there are yet further reasons that have appeared to make one wonder about the existence of the interior. One is that, once you go beyond uncharged static black holes, if you go to the more realistic case, more generic case where the black hole has some rotation or has some charge, then you see that in addition to singularities, you also have a new phenomenon of Cauchy horizons already at the classical level, that there are surfaces in the interior of the black hole beyond which causality breaks down, and the classical equations don't allow you to predict what comes past a certain region in the interior. And then famously, Hawking discovered that there were more puzzles that happened when you took quantum mechanics into account. So Hawking in the 1970s discovered that black holes radiate due to the interaction of their gravitational field and quantum effects. And as they radiate, according to the standard picture, the interior gradually disappears until the black hole disappears, and one is just left with the exterior space-time again. And it seems, I'll discuss this more later when we compare and contrast with the black mirror, that there's an information puzzle, that quantum mechanics is unitary. The evolution is unitary and reversible in principle. There should be no loss of information. But it seems that the information that falls into the black hole crosses the event horizon and winds up at the singularity, is then causally disconnected from the exterior space-time that's left over after black hole evaporation. And so what gives? It seems like there's a contradiction in the standard picture. There's another more modern variant of this puzzle called the firewall paradox. There's another question, which is that, another thing you might wonder about is that, so according to the classical picture of a black hole, if I drop matter into it, as an external observer, I have to wait until t equals infinity for that matter to cross the horizon. According to my clock, it looks like I'll have to wait for an infinite number of ticks of my stopwatch before I see the matter cross the horizon. On the other hand, Hawking tells me that as a distant observer, I'll only have to wait a finite number of clicks of my stopwatch before I see the black hole evaporate and disappear completely. So, is it really true that the infalling matter managed to cross into the interior? If somehow before it even got to the horizon, the whole thing evaporated, it seems to cast doubt on, again, whether the interior is real. And then a final puzzle, which I don't hear talked about a lot, but which seems puzzling to me, is that a conventional view is that all global symmetries are violated by black hole evaporation. Because let's say I make a black hole entirely of baryons, I make it entirely out of neutrons, let's say. So but then when it evaporates, almost all of the evaporation is in photons that carry no baryon number, and so the baryon number has to be violated in the evaporation of the black hole. And you might say, well, maybe that's not such a big deal because we think baryon number is not an exact symmetry. It seems like a classical symmetry of this, an accidental symmetry of the renormalizable part of the standard model, but we know it's anomalous. And so even if the evaporation, even though the violation of baryon number might be very exponentially tiny in conventional circumstances, it's maybe not so implausible that under extreme circumstances like a black hole, that evaporation would be more that violation would be more important. But then what about the other global symmetries that we know of in the universe that are not anomalous and that could very well be exact for all we know? One example is baryon minus lepton number, which has no anomaly in the standard model of particle physics as we know it. And again, for all we know, that could be exact. Do we really think that even if there's an anomaly-free symmetry of nature, that somehow magically gravity violates that? It seems puzzling how that would work. And CPT is another example of a global symmetry that we don't think is anomalous. Okay, so I'll come back to this at the end. These are all issues that that might make you wonder about the normal black hole, and that, in a sense, seem to have more natural explanations in the black mirror picture. Okay, so how could one get to a new picture? What should the new picture be? Well, for that, I think it's helpful to take a little aside from classical analysis and think about Gibbons and Hawking's argument for calculating the temperature and entropy of a black hole. So I'll remind you, this was in the mid 70s. They had this paper where they switched. Let's say we start from the Schwarzschild metric again. Let's make the change of coordinates from r to sigma, just like Einstein and Rosen did. But now, in addition, we'll let us Wick rotate the time. We'll define a new, instead of the original Schwarzschild coordinate t, we'll switch to a new Euclidean time coordinate tau, related by t equals minus I tau. Then, if we rewrite the metric in that language, it's purely positive definite. It has all of its eigenvalues are now +1, so it's like a positive definite metric, not a Lorentzian metric anymore. So that's called the Euclidean Schwarzschild metric. Satisfies the Euclidean Einstein equations. And now if we simplify the metric and focus just on the region near the horizon, near sigma equals 0, then the metric that we get, we find, is really the metric for a cone. Okay, so these two coordinates describe the metric of a two-dimensional cone. The blue, what I've shown is the blue cone here, times a sphere, times a two-sphere of radius 2m, sitting at every point of the cone. And so they noted that if you take this cone and then you periodically identify the time coordinate with a particular period, 8 pi m, then the conical defect at the tip of the blue cone is removed, and you get this nice smooth space-time. The right-hand blue bowl. And so they argued that they argued that because periodicity in the imaginary time direction is related to thermal equilibrium, that they could then infer from this argument that the temperature of the black hole was 1 over this period, 1 over 8 pi m. And then they also argued that by calculating the action on the right-hand blue bowl here, they were able to infer, again, by using the relationship between the path integral and the Euclidean version of the path integral, they were able to calculate the entropy of the black hole, and get a non-zero value, the traditional entropy of the black hole, which is the area divided by 4 in Planck units. Okay, but again, there's something funny about that, which is that, you know, we Wick rotated our space-time, and then we ended up with this blue bowl, which seems like a complete space-time on its own, but it seems to only describe the exterior of the black hole. And you might ask, what happened to the rest of space-time on the other side of the horizon? Where did its Wick rotation go? You know, do we, you know, in Lorentzian, we don't think the horizon is the end of space-time. So you might go back and say, well, wait a minute, could we have been missing something in our original argument if we wanted to describe what was going on the other side of the horizon? And well, you see, you know, here the answer is yes. We have a cone here, and of course, every cone has as its natural analytic extension a kind of double cone where we, again, just like Einstein and Rosen did, but now in the Euclidean context, we just let the coordinate sigma, we don't truncate it at sigma equals 0, we just let it extend to negative values, and we get the double cone now, shown here with both a left red part and a right-hand blue part. And now if we impose this period, the period that smooths out the tip, you know, we see that we don't just get a single bowl, we get two bowls that still share a common S2, this purple S2, in common between them. So they're joined at a two-dimensional sphere, which is the two-dimensional sphere of the horizon of the black hole. Okay, but you see, now we have a complete analytically extended space-time, but in the Euclidean case, it's clear there is no further analytic extension to be done here. This is now the whole space-time in the Euclidean sense. So we've analytically extended, we've gotten the full maximally analytic extended solution now, but there's still only two exteriors, the Euclidean version of two exteriors. There's still nothing corresponding to the interior of the black hole. So what if we Lorentz transform back if we Wick rotate back, excuse me, to Lorentzian signature and ask, what is this all saying in Euclidean in Lorentzian signature? Okay, then, well, as I was mentioning, if we go back to ordinary time t, go back from tau to t, then we just get back to the Einstein-Rosen bridge, the Einstein-Rosen wormhole solution we discussed before. And now the question is how to complete it, or how to complete it. Is there a way to complete it that makes it correspond more naturally to the Euclidean solution, which had no interior? The conventional completion is to switch to so-called critical coordinates, and then we get this whole diagram here with two exteriors and two interiors and the singularities we mentioned. But is there another way? And yes, there is. If we wanted to kind of parallel the Euclidean picture properly, there's another topologically distinct possibility here, which is the black mirror. Okay, so how does it work? Well, so let's just, you know, previously we discussed two different famous coordinate transformations, r to sigma, the Einstein-Rosen coordinate extension, and t to v, the Eddington-Finkelstein change of coordinates. Let's do them both. So here we've already done the sigma transformation. Now let's also replace t by v in the same way that Einstein and Rosen do. And so what happens? Well, we get this new version of the metric, and these new coordinates now, in addition to the right-hand exterior now being extended across the black hole horizon into the upper interior region, we also find that the left-hand exterior in these coordinates is also extended down into past this lower black hole horizon into the lower interior. But we notice something funny, which is that if we do the extension this way, that although we've seemed to cover the whole space-time, a problem is that we've now, if we consider 2 points on the horizon, a point up here and a point down here, it looks like we've assigned the same coordinates to 2 different points in the space-time. Because remember, over here, in this region over here, sigma is negative, and in this region over here, sigma is positive. But up here, sigma is equal to 0, and along this horizon, v runs from minus infinity to infinity. And down here, sigma is also equal to 0, but v runs from minus infinity to infinity. So if we don't want to assign 2 different points the same coordinate, we see we're forced to identify a point on the upper horizon here with a point on the upper horizon here. That solves the problem. Now we assign each point in the space-time a unique coordinate. But we see that same identification suddenly removes the interior. Well, let me first say something here, which I forgot to mention, which is that, okay, so I've shown the extension, this extension here, the blue and purple extension shown in the figure here, is how the interiors get extended if we switch to ingoing Eddington-Finkelstein coordinate v, the one which covers the black hole horizons. The other possibility is to extend the coordinate by switching to the outgoing Eddington-Finkelstein coordinates, v minus. That covers the white hole horizon, so it extends the coordinates in this different way. And if we do this extension, we find similarly that if we want the coordinates to be uniquely assigned to space-time points, we don't want to assign 2 different points the same coordinate. We also have to identify each point on the white hole horizon with the antipodal point on the opposite white hole horizon. But now, if we do both of those things, we arrive at this picture, okay, where okay, so I've shown here that I'm showing here that each point P on this horizon is identified with its corresponding antipode P prime on the opposite horizon. Q is identified with Q prime. Also on the white hole horizon, R is identified with R prime, S is identified with S prime, etc. But now, if we identify things in this way, the upshot is that we've glued the two. If we identify things as indicated by the analytic extension we get in sigma v coordinates, it means that we've glued the 2 exteriors to one another, and that now the interiors have been completely removed. There's no way to somehow extend the space-time to obtain the interiors, because if we look at this horizon, it's a surface. It's a codimension 1 surface in space-time. It has only 2 sides to it. And on one side, we have this exterior. And now on the other side, we have this exterior. So there's no way to glue an interior to the same surface. That would have to have 3 sides. So this is, in short, the black mirror. This is just the idea in brief. It's one way to motivate it. That it's just another topologically distinct analytic extension of Schwarzschild's original exterior black hole. And I say analytic because you see that in these coordinates now we're letting v and sigma run from minus infinity to infinity, just like Einstein and Rosen did. And the action is now the line element, excuse me, is now a completely analytic function over that whole range of those coordinates. It has no coordinate. It has no curvature singularities anywhere. It's a vacuum solution of Einstein's equations. The Ricci tensor is 0 everywhere. The Einstein tensor is 0 everywhere. So it's just a topologically different, distinct analytic extension. Now, that all sounds interesting, but it's important to mention that there's no free lunch. So if we look in these V sigma coordinates, if we look at the 4 eigenvalues of the metric, as we follow the metric up to the horizon, we find that 2 of the eigenvalues pass through 0 at the horizon. Okay, so there's the 2 angular eigenvalues remain finite. These are the 2 eigenvalues on the 2 sphere. So the 2 sphere remains completely regular. But in a normal Lorentzian metric, you have 3 positive eigenvalues and 1 negative time-like eigenvalue. So 2 of them are the 2 positive eigenvalues on the 2 sphere. But then the remaining 1 positive and 1 negative eigenvalue, what happens is that they both, as how to draw this with my hands, as sigma goes from negative to positive, they cross, and the eigenvalue that was the negative eigenvalue on one side smoothly evolves to be the positive eigenvalue on the other side of the horizon, and vice versa. The eigenvalue that was the positive spatial eigenvalue on one side of the horizon smoothly evolves to become the negative eigenvalue on the other side. So that's what I've shown here. So if you look at sigma equals 0, as you pass from sigma negative to positive, you'll see that both of these functions, both of these eigenvalues, lambda plus and lambda minus, have a simple analytic 0 at sigma equals 0, but they cross with one another, and they satisfy this symmetry. So one eigenvalue is basically swapping with the other one as we cross to the mirror image side of the horizon. So we're used to the fact that in an ordinary black hole, that if your metric has some eigenvalues that become 0 or infinity as you get to the horizon, which is what happens, for example, in the original Schwarzschild coordinates, no problem. We're just supposed to change coordinates, and you can find a new coordinate system where all of the eigenvalues are completely non-singular and neither 0 nor infinity. But here that's not the case. You have a choice. If you want the eigenvalues to all remain finite at the horizon, then the Kruskal extension is the unique analytic solution, and you're led to the black hole interior. On the other hand, if you want to avoid the black hole singularity, you want to avoid the various problems associated with the interior of the black hole, there's this other topological possibility where you paste the 2 exteriors together. It is perfectly analytic. There's never a curvature singularity. The Ricci tensor remains 0 at all times. But if in any coordinates in which the metric is smooth and analytic, like these sigma v coordinates, you have this issue that 2 of the eigenvalues cross. It's a genuine topological property of the space-time. It's a real thing about this solution that can't be avoided. So it's more like the poles in the propagator of the Feynman propagator that you have to go around when you're defining the Feynman propagator. It's a real singularity, and it's part of life, and you have to go around them in the complex plane, basically, if you want to make sense of them and not just plow singularly through them. So that's an important thing to emphasize about the black mirror. So far I've been discussing the uncharged, non-rotating black mirror, the Schwarzschild black mirror, if you want. In our paper, we give the more general charged rotating solution. So this is the most general stationary black mirror. I won't go through this in detail, but just to briefly say, so basically you can express the line element in terms of these tetrads, these tetrad 1 forms, epsilon A and epsilon B. And you can also express the field strength, the electromagnetic field strength 2 form F in terms of the tetrads E twiddle. Here explicitly is how the tetrads E twiddle are given in terms of the 4 tetrads are given in terms of the coordinates. These are expressed currently in terms of V and R coordinates, okay, and theta and phi. where these functions, these functions delta sub theta and function delta sub r here appearing in the metric. These are defined as usual. These are familiar functions from the Kerr-Newman solution of the black hole. So far, this is all expressed in the analog of Eddington-Finkelstein coordinates, R and V. And now to get the black mirror, we just have to do, again, the final extension, which is to switch from R to sigma, as we did before. So in the general case, to define R, the extension from R to sigma is just R is equal to R plus the radius of the horizon of the black hole in Boyer-Lindquist coordinates, plus sigma squared. Okay, and then again, now once we've made that change, if we just let R run from sigma run from minus infinity to infinity, and V run from minus infinity to infinity, then exactly the same qualitative story happens as before. We find that there are points on the horizon, two different points on the horizon that are assigned the same coordinate in these coordinates. If we want to eliminate that doubling, we identify those points, and in that way, we've identified the two exteriors at the horizon and eliminated the interior as before. So that's what the black mirror is in brief. So what are some reasons to be interested in it? Why should you take it seriously as opposed to the traditional black hole solution? Well, one thing to say is that first thing to point out is that it would be the relevant path integral. It would be the relevant stationary point of the path integral if the boundary conditions for the path integral were CPT-symmetric. So here I've schematically sketched. So if you're trying to look at paths that interpolate between a certain state I at past null infinity and a certain state F at future null infinity, but also in order to have a CPT-symmetric solution, you also demand the CPT conjugate of F as the boundary condition at the other exterior, at the antipodal exterior to this one, and the CPT conjugate state I bar as the boundary condition at the CPT conjugate exterior to the initial one. Then this black mirror solution is as we show in an appendix of our paper, it is first of all a stationary point of the action, and it is the relevant stationary point that satisfies these boundary conditions, and doesn't have any other boundaries. The usual black hole is even if you took a CPT-symmetric version of it, even if you put CPT-symmetric boundary conditions at the exteriors, you have these other boundaries if you want, but they're singular, and you don't know what to specify there or how to specify it really, because there's really singular surfaces that are supposed to be excised from the space-time. Yeah, and so here I've drawn a picture of what physically it means to have CPT-symmetric boundary conditions. It means if I have a particle falling in here along this trajectory, and the arrow shows the direction of its proper time or its charge flow, then there's a corresponding particle following the mirror trajectory up here, but its arrow is reversed. So what it looks like is that there's a particle falling into this black hole horizon, while its corresponding antiparticle is falling into the same point at the same time on the corresponding other side of that horizon. Okay, so much for stationary black holes. Let me try to describe then what the story is for the dynamical black hole. Just like for ordinary dynamical black holes, we can't in general give the solution analytically, but we can draw what the Penrose diagram will look like in the same way that we can for the ordinary black hole. So for the ordinary black hole, if it's not stationary, if it's formed by dynamical collapse, we get a space-time diagram like this. Okay, and it only has the black hole horizon. The white hole horizon we think of as a kind of not real artifact of stationarity. But okay, that's the black hole. If we want to get the black mirror, well, again, what we're supposed to do is take two of those exteriors and paste them together at the horizon. So that's what I've done here. I've taken two copies of the exterior and pasted them together at the horizon. Now it's a bit weird, this way of drawing the diagram, because time runs up in this direction, but sideways in the other exterior. So it's more physical to fold the diagram so that now you can see. So now in this diagram, time runs up on both sides. Both sides are, in other words, both exteriors view this horizon as a black hole horizon. So it's a null surface to their future. And so here you can see this picture where a blue particle is falling in from one exterior and meeting its corresponding antiparticle, which is falling in from the other exterior. Now you might ask, what happens when they meet each other? And so here I've drawn that. Well, it seems like the only possibility is that they annihilate, like particles and antiparticles do. But if they annihilate into radiation, there's only one way for that radiation to go. If it's going to propagate in if it's going to propagate in the time-like direction, if it's not going to propagate backwards in time, which is that it'll flow up the horizon, which is that's the only way forward for a particle on the horizon. So that's what the green line is representing here, the annihilation radiation traveling up the horizon. That would be the classical picture of a collapsed black hole. So what about if we take evaporation into account? So here is the normal diagram that people draw to describe an evaporating black hole. This roughly speaking, this region is before the black hole has evaporated, and then this region up here is supposed to represent after the black hole has evaporated. So here I've drawn it a bit more in detail to show how that can happen. We see that if effectively the horizon curves up a bit, then radiation can gradually escape from the horizon, and that's why the black hole is losing mass. Okay, so the corresponding black mirror again would be two of these spacetimes, two of these exteriors pasted together at their horizon. But now it's this curved horizon. So the matter that falls in annihilates with its antimatter and turns into radiation, which rides up the horizon. But now, because of quantum mechanics, it can't be exactly localized on the horizon, so it won't ride along forever. It gradually leaks off, and that's what black hole evaporation is. But you can see here what one of the advantages of this picture. I mean, it's just very it's easy to see from a picture the advantage, which is that the usual information paradox is just that if quantum information is carried along to the horizon here, to the singularity here, that this singularity is just out of causal contact with the future region where the black hole has disappeared. I mean, any curve connecting this point to this point has to go faster than the speed of light. So it seems to involve superluminal transfer of information from inside the black hole to outside the black hole. Whereas in this picture, you just never run into that problem. I mean, the information is always stuck to the horizon and rides up the horizon until it leaks off again. But at no point does it have to travel superluminally to make it to Scri+. So we also think it fits nicely with the picture, the CPT-symmetric picture of cosmology that we've been interested in. So to describe briefly the idea, if you look back, when we look back with our telescopes toward the Big Bang, we see the cosmic microwave background. Cosmic microwave background, its temperature power spectrum has this famous ringing pattern of peaks and troughs. If you ask, what is that? Why is there a ringing pattern of peaks and troughs? Why are there the oscillations? Why are the peaks and troughs at the particular L values they are? It's exactly because if you take any individual mode of the density perturbation, it's oscillating, but if you follow it back in time, it was exactly reaching its peak of oscillation with zero time derivative right as you get back to t equals 0. Normally in inflation, people who believe in inflation describe this a different way. They tell a story where, okay, actually you don't follow the oscillation back to t equals 0 in the radiation dominated era. You follow it back to t very close to 0, a tiny fraction of a second, and then you replace radiation dominated era with an inflationary epoch. And the reason that the modes, the density perturbation started with zero derivative was because supposedly they got stretched out of the outside the horizon during inflation and frozen. But anyway, the point is that everyone agrees that the basic initial condition is that at the start of the radiation era, the all these density perturbations were reaching the we're all in phase, we're all in sync, we're phased up with one another, so that they were all exactly at the peak of their oscillation, peak amplitude with zero time derivative as you get back to the beginning of the radiation era. One of the main motivations for our work is just to say, well, you could tell an inflationary story about that, but there's a simpler interpretation of what one is observing then, which is just that, those perturbations are all satisfying a reflecting boundary condition. They are satisfying exactly a Neumann boundary condition, just like certain components of the field, of the electromagnetic field, satisfy it in an ordinary mirror, which is why you see a copy of yourself on the other side of that mirror. So it's just a simpler interpretation of what's going on, of the same fact. And so we've just gotten interested in taking that interpretation seriously and gotten more and more excited that because we think it gives alternative, kind of more rigid and elegant explanations for various facts about the universe that are usually attributed to inflation in one way or another. But in any case, for the present purposes, if you take that picture seriously, then here's a picture of here's a Penrose diagram of the cosmological space-time. Okay, this outer sheet is this outer sheet of this sort of double cylinder is our universe. We're following it back to the bang. Here's the surface of the Big Bang here. Now, if the Big Bang is really a mirror, which is what it seems to be from the primordial cosmological perturbations, we know that there's two ways to think about a mirror, and you learn in electromagnetism that there's two ways to understand the fields on your side of the mirror. You either can say, oh, there's actually a piece of glass there with silver atoms on it, and those silver atoms are just making the fields obey a certain reflecting boundary condition as they get to the mirror. But an alternative picture, which gives the same answer on your side of the mirror, is to say, no, there's no mirror there. But to use the method of images, you say there's no special surface or material in space-time, but there's just a mirror copy of the world with opposite charges on the other side of the mirror. And that's what explains what the reflecting boundary conditions I see. So if we take that second perspective, the kind of method of images perspective, then in addition to our half of the cylinder, there would be another half on the other side of the bang. And here I've just taken that other half, that bottom half, and folded it up inside to picture it as being next to so there's an inner cylinder and an outer cylinder that form effectively two sheets of space-time with CPT-symmetric matter content on them. And if you take that perspective, then well, now it's kind of easier to understand where these black mirrors are coming from. I mean, you might wonder, okay, am I really supposed to believe that as matter collapses to a black hole, that when the event horizon forms, suddenly magically another mirror exterior of the universe appears on the other side of that newly formed event horizon? It sounds maybe implausible according to the traditional perspective, but if you appreciate that there are really two mirror sheets of space-time next to each other, and that when matter is collapsing to form a black hole on your side, at the same time, antimatter is collapsing to form an anti-black hole on the other side, and then there's no mystery about where the other side came from when the two black holes form. It's just that the formation of the horizon is exactly the connecting of those two sheets. So that's what I've shown here. I've just shown a modified version of the space-time where a couple of black holes have formed here and here, and you see their event horizons coming out at the speed of light, but the event horizons are also where the two sheets join. And I've just drawn another picture of the same thing here. So here's a little zoom in of two sections of the two sheets, and here we have a cloud of matter on one side before it has collapsed, and I've also given it some electric charge, some, let's say, positive net charge. And then here's the corresponding antiparticles on the other sheet with negative charge, and then they begin to collapse, and so the embedding diagram begins to bend into the embedding space-time. And then in this picture, the formation of the event horizon is the merging of these two sheets of space-time. So it's not that the mirror exterior suddenly comes into existence in this picture when the black hole forms. There's another sense, this kind of method of images sense, in which it was already there all along. That seems to be what the reflecting boundary conditions at the Big Bang suggest. And this is just those two sheets remerging. Okay, so I'm almost at the end here. So let me just come back and revisit a few of these initial puzzles with the traditional black hole and see how they look now in terms of this black mirror solution. So first, if we look back at Einstein's objections, that there's an interior that seems to be hidden from, in the traditional picture, an interior that seems to be hidden in principle from observation. Now that interior is gone, so we might feel more comfortable about that. There's in the normal interior, there's a curvature singularity. Now we have a new solution with no curvature singularities. The Einstein equations with r mu nu is equal to 0, or g mu nu is equal to the Einstein tensor capital G mu nu is equal to 0 everywhere in the new solution. The Cauchy horizons that you find in normal rotating or spinning black holes, which connect you get these Penrose diagrams that have in addition to the two exteriors at the bottom, a whole infinite series of exteriors with wormholes connecting them. That all goes away, separated by Cauchy horizons, so you can't predict the evolution from one region to the next. That all goes away. Those were all disappeared when the interior disappeared. I described a moment ago how the information paradox is improved, because if there's no interior, there's no need for superluminal propagation for the information to escape from the interior. I had described before this puzzle about whether a black hole evaporates before it forms, and should that lead you to be skeptical about the existence of the interior. In this picture, yes, it should, and so the interior has gone away. And finally, this question of whether whether this puzzle about how traditionally black holes violate global symmetries, even if they're completely anomaly free and appear to be exact, um, we don't run into that problem anymore because we see that if we throw a baryon in from this side, a corresponding antibaryon comes in from the opposite side and annihilates. So from a global standpoint, there actually is no violation of that global symmetry uh, in the formation and evaporation of the black hole. The total baryon number in that process is zero before and zero afterwards. Okay, that's all I wanted to say. Thank you very much for your attention.
Great, wonderful. It's really fascinating lecture, Latham, and definitely understandable. And I think there's lots to discuss. So please, for asking questions, use the raise hand icon. And while you get ready, I think I also have many questions for Latham. Maybe could I begin by asking, where is the second exterior space? Is that hidden from observation? I mean, do we see it in today's universe?
Uh, you don't see it, but mirror you sees it. It's the other side of a mirror. So in this picture, you still can't receive a light signal from someone in the other exterior,
Mm.
but the other exterior is a mirror copy of what's on your
Yes,
exterior.
sir. Is this suggesting an extension of space-time dimensionality from 4 to 6? On the horizon, there's a S2 that leaves 2 on my side outside the horizon. And if I make a mirror, am I to think of having generated 2 extra space-time dimensions, 2 plus 2 plus 2, 6? Or am I still in a 4-dimensional space-time?
You're still in four because it still takes four coordinates to specify where you are anywhere on the mirror.
Mhm. Okay.
Yeah.
So yeah, that mystery is still there. Why 1 time and 3 space? Why not 3 times and 3 space? Yeah.
Yeah. It is interesting that at the horizon, the just like in the Euclidean picture, where at the horizon the cone shrinks from a 4D cone to a 2D sphere and then grows back to a 4D space-time. So at the point where the two cones meet, it drops dimension to 2. Same thing happens basically
Okay.
here. This fact that I was mentioning that two of the eigenvalues of the metric drop to 0, and so correspondingly two of the eigenvalues of the inverse metric have poles. Uh, it's basically saying that the dimension of the space-time drops to that same 2 sphere, which at the horizon. So there's in a sense the horizon has 2 dimensions.
Okay. Yeah.
Is a two-dimensional surface, which is kind of what you would normally think, because it's normally you think of it as a 2 plus 1 dimensional surface, but one of those dimensions is a null direction along which
I
the
agree.
metric is 0. So,
Mhm. So if I'm an infalling observer with a collapsing star, say in the Oppenheimer-Snyder solution, so what am I going to see now?
I think unlike an Oppenheimer-Snyder, you would run into the infalling matter would run into its antimatter and annihilate. So that's the distinction.
So
You'll
try to write down the Oppenheimer-Snyder solution now in GR, let's say using your coordinates with sigma as well as v, I'll see something different from Oppenheimer-Snyder, is it?
Yeah, because you'd have to put in a CPT-symmetric initial state in which
Mm.
you have infalling Oppenheimer-Snyder matter on one side and antimatter on the other side, and when they meet
Okay,
each other, they'll evaporate.
great.
They'll meet each other at the horizon.
Great. Thank you. Thank you so much. Tavian, please go ahead.
So thank you very much.
Hello, Devian.
For very interesting talk. Um, I've got some questions that you kind of hit the nail on the head just a minute ago with your comments about dimensionality. There's a difference between topological dimension and the metric behavior. Am I correct that the metric is degenerate at sigma equals 0?
Yeah, exactly. That's what I was saying. That the two of the eigenvalues go to 0, and so the metric is degenerate in those coordinates. And what I was saying is that if you want the metric to be smooth across the horizon, that is unavoidable in this solution. That there's a so it's a bit it's analogous to, so Neil and I have been interested in in cosmological spacetimes where you, if you imagine following this FRW spacetime back to the bang, you can analytically extend it through the bang by just letting the conformal time extend to be negative. But the sign that there's something non-trivial in the pasting, topologically non-trivial in the pasting between the space-time after the bang and the space-time before the bang, a kind of orientation flip actually, is that the metric is forced to degenerate in any coordinates which are smooth across it.
I understand in some sense degenerate metrics better than I understand a notion of change in the topological dimension of the underlying manifold.
Yeah.
Is there a claim that the dimensionality is actually changing?
No, no, and that's a very good point. And another thing to say, it's something that Neil and Costas and I are interested in and are working on right now, is about, I mean, there are these techniques that are well developed techniques in algebraic geometry for where you're always dealing with algebraic varieties that are defined as the solutions of some sets of polynomial equations, and those defined surfaces which have singularities in them very closely analogous to these singularities that appear at the black hole or horizon or at the Big Bang. And there are well-developed techniques for so-called blowups of those. There's a basically unique blowup of such a singularity where you maintain the you maintain the dimensionality of the surface. It's just that you can think of it as a non-singular surface embedded in a higher dimensional space in a canonical way.
So
And the degeneracy of the metric in that picture is coming from a kind of singular folding of how the surface folds in the higher dimensional space compared with the projection down to the usual space-time dimension.
You've led nicely into my last question when you mentioned uniqueness. Because of the degenerate metric, presumably, that's how you get around lack of existence in uniqueness or the ability to have a different extension across the horizon. But I guess the question will come down to what do you put in order to get out some notion of a unique mirror solution out?
Yeah, well, the other thing you're right. That's right. So the one of the nice things about the blow up is exactly that it has a kind of that there's a canonical blow up associated with a singular algebraic variety. Also, I should say though that the other thing is just that I think analyticity, I think even before you blow things up, that if you have a singularity where everything is where the only singularities are poles and manifest as poles in the inverse metric or in the curvature, then I think that the analytic extension around those is unique for the same reason that the analytic extension around of a holomorphic function around a pole is unique.
If you're going to go there, I'm going to have to say I don't think I understand curvature for a degenerate metric.
Mm-hmm. Well, it definitely it's like understanding a holomorphic function at its pole. It's not defined at the pole. It's just defined everywhere around the pole, the complex plane.
Okay.
So I agree that the curvature. Well, the curvature can blow up um, uh, at the degenerate point, which is what happens in the Big Bang case. Well, yeah, there's components of the curvature that blow up there. Um, now, in this black mirror solution, actually the curvature doesn't blow up there, but nevertheless, there's a pole in the inverse metric, which so it's really the inverse metric in that case is really not defined there, I would say.
Okay, thank you.
Yeah.
Thank you. Wei-Ning,
Thanks
please
for your
go.
question.
Hello, thank you for the
Hi,
talk.
Wei-Ning.
Actually, I always have these questions for CPT-symmetric universe. Is that how symmetric it is? We can imagine it is globally CPT-symmetric, but um, this work, it seems like you're saying not only globally, the universe is not only globally symmetric, but also locally symmetric, because black holes are kind of like some local structures or events. So this work seems arguing that our universe and the anti-universe um, have symmetric in black hole scales. So, for example, if in our universe there is a black hole formed, then there is also another anti-black hole formed in the other universe. But it's just hard to imagine because it kind of like break the causality. So why are what's happening in our universe will kind of affect what's happening in anti-universe?
Yeah, very good question. So first of all, this is something that Neil and I have been trying to find the killer argument about. In other words, there's two possibilities. One is that, what we see is a kind of, as I say, it seems to be that the primordial perturbations we see are saying that there's a reflecting boundary condition at the bang if you just don't think about inflation and just follow radiation domination all the way back to the bang. Now, one interpretation is that it's only classically mirror symmetric, but that quantum mechanically in the path integral you allow paths that may not individually be, you're summing e to the I action over paths that are not individually symmetric. And it's just that if you impose CPT symmetric boundary conditions on those path integrals, then the stationary points that end up corresponding to the classical spacetimes you see are symmetric because of the boundary conditions, even though the paths that you're summing over are not. The other possibility is that the other possibility is that the actual paths should be restricted to be CPT symmetric, in which case it's really more like you're saying that the two halves of the universe are kind of a redundant description. They're really, it's like the mirror universe that you see on the other side of an ordinary mirror. You don't think there's a real mirror there. You don't think there's a real other person on the other side of the mirror. You just think of it as a an illusion, but they don't have any independent freedom to be anywhere else. So like you were saying, if a black hole forms on a certain spot on our side, then if the other side is really redundant, then it'll be forming in exactly the same spot on the other side. But yeah, whether the other side of the universe should really be thought of as merely approximately a mirror symmetric thing in a statistical sense, let's say, or in some global sense, or whether it should really be thought of as a locally exact copy. Indeed, this picture that I gave of black hole, interpreting the black mirror as essentially the rejoining of the two sides, seems to argue for the locally exact version of it. I must say that we have other arguments that kind of suggest the other way and suggest the other possibility. And I personally have not. I personally don't feel completely certain about which of those two things is correct yet. But anyway,
If the
but it is.
second possibility is correct, then would annihilation still happening? Because the second argument seems to
No.
say the mirror universe is not real, right? It's just
Yeah. So just to come, so before I go there, let me just go back to your you had a question about whether there was some problem with causality about that. So remember in this picture, the thermodynamic arrow of time flows away from the bang in both directions. So on neither side can an observer send a message to the other side. But we think there may be a picture where these solutions are being picked from a path integral. You know, it's kind of our variant of Hawking's proposal for the wave function of the universe, that we have a proposal that the wave function of the universe could be that the amplitude for such and such a 3 configuration up here is the sum over all 4 configurations that interpolate between that 3 configuration and the CPT-symmetric 3 configuration down here. And it is plausible that the stationary points of that path integral are locally symmetric in the sense that you described between the two sides, without having to say that there's symmetric that there has to be any causal contact between the two sides. But yes, and then just to come back to your subsequent question, right? If the picture that I mentioned about particles and infalling particles from one side annihilating with infalling particles from the other side, and thereby saving conservation of global anomaly-free global charges is correct, then, like you say, that seems to require that things be locally true local mirror images of one another on the two sides. Yeah, thanks.
yeah.
Good question.
Okay, thank you.
Thank you. Anthony, please go ahead.
Hi, Latham.
Hi, Anthony.
Hi, thanks very much for the talk. My first question is related to what you've just been talking about with Finding, and it's really on the question of what might be the observable differences in this view of what a black hole is. I'll call it a black hole, even though you really mean a black mirror here. So what are the observable
I'll allow it.
in this as against, a standard view that an astrophysicist might have of a black hole? Is it this thing about you expect there, anytime you attempt to throw something in, it is met by an antiparticle coming from the other sheet and the two annihilate, and so you get this radiation at the horizon? Is it that's basically the only difference? And in any case, that is the same as the Hawking radiation, you're saying?
Yeah, also good question. So we're wondering about that too. One thing to say is that a key question, which we don't really know the answer to, but we speculate an answer in our paper, is that, for a stationary black hole, the event horizon and the apparent horizon, there's various different ways to various different markers of the edge of the black hole, and they all agree in the stationary case. But in the dynamical case, they don't agree. So, for example, the apparent horizon and the event horizon are in define different surfaces in a dynamical black hole. But in that case, you might wonder which of those. And so when you get to the dynamical case, you should wonder, are the two mirror images meeting at their event horizon, or are they really meeting at their apparent horizon, or something, some other surface? We think it's maybe a little bit unlikely that they're meeting at their actual event horizon in the dynamical case, because that's a kind of teleologically defined, or I'm not even sure what the right word is, but you need to know the future history of the space-time and then trace light rays back from Scri plus in order to even determine where the event horizon is. So it seems a little bit implausible that that's really where the two sheets are meeting. So we suspect, and we give, there's a little bit of evidence for this coming from a nice recent paper by Wald and Hollins on defining entropy and the first and second laws of thermodynamics for dynamical black holes. That maybe the right pasting surface is the apparent horizon, but again, we don't feel sure about that. It could be some other surface where the two sides meet in the dynamical case. But the point of all of that is that the fact that those meeting surfaces, like in the case of the apparent horizon, differ from and lie outside the event horizon mean that in the dynamical case, yeah, there may be room for signals to escape from the meeting surface into the exterior universe. Maybe gravitational wave echoes, or who knows what exactly. That you wouldn't see, if you focus on the stationary case, it would look like there's no observable difference between the two cases. But we are holding out hope that in the case of dynamical situations, two black holes merging or something like that there could be real differences. I think you're muted, Anthony.
I apologize. I've got a phone call that I've got to accept. Sorry about
that. Oh, okay. No problem.
Okay,
nice to see you.
Go ahead, Yuri, please.
Oh, yeah, thank you. Can you hear me?
Hello, Yuri. Yeah. Yes.
Yeah, hello. My name is Yuri. I'm from Kiev. Yuri Shtanov is my name.
Nice to meet you.
Thanks for a nice talk. Yes. You mentioned and stressed several times that your metric is no longer smooth across the junction. You're gluing horizon.
It's smooth in the sense of analyticity, but it's not. But the eigenvalue degenerates.
No, if I'm not mistaken, you might correct me if I'm mistaken. It's actually it's continuous, but its first derivative is discontinuous.
No. It's all the derivatives. It's infinitely many derivatives are continuous. It's smooth.
Oh,
in V sigma coordinates. In V sigma coordinates, it's perfectly analytic.
I'm not sure about that. I think. Well, please do
go try checking it. It is.
But if I'm
Let me show you.
If I'm right, no. You see, if it's smooth, that means infinitely derivative.
Mm-hmm.
Then it should be a continuation of the usual Kruskal extension of the Schwarzschild, which should go inside the black hole region. That's what you have actually said in your talk. If it's smooth, then it's the only extension is the Kruskal extension.
It's the only non-singular extension. So if it's smooth and all four eigenvalues are non-zero, then the only extension is the Kruskal extension.
If you extend the metric smoothly beyond the horizon, I mean smoothly, well, it's sufficient to have second derivative continuous. Then it's a Kruskal extension. In your case, you're just gluing. You see, you're reflecting your metric backwards, right? So you're creating discontinuity in the second derivative. Please check this. And if I'm right, then you're creating a singularity in the curvature, like delta function.
I'm afraid that you are not right. Could I respond?
Yeah, sure.
So here's the metric. You see it is smooth. You see how everything is. You can see what the metric is here. So R is given by this function. So you can see sort of by eye that everything is smooth.
Yeah, but something has to change signs. Sigma has to change sign. or the sign in front of sigma has to change. I think when you cross it.
No. So this is the metric, and you just are letting sigma and v run over all values from -infinity to infinity. So you can see explicitly here that the metric components are all smooth. But the thing you're thinking about, the theorem is that if you see there's an implicit assumption in the usual statement that Kruskal is the unique extension, which is that it is the unique extension if it's the unique non-singular extension, meaning that at every point you can find coordinates where all 4 eigenvalues of the metric are non-zero.
Yes.
So this is not a non-singular extension in that sense. If you want to describe the black mirror in smooth coordinates, then inevitably you have this issue that 2 of the eigenvalues pass through 0 at the horizon. So that is why we can get a different extension. That's why the normal Kruskal uniqueness theorem doesn't apply. And so it's like I was saying, there's no free lunch. We get a different sort of singularity, a milder singularity than the one in the normal black hole. There's no curvature singularity,
So
but there is this.
So what kind of singularity is that? If I'm sitting at the point P, for example, and I want to construct an open region around P, which covers part of 1 and part of 1 prime, can I do that?
Yes, but so this one way to say it is that the singularity is that the inverse metric, the 2 of the eigenvalues have poles at that point.
No, but so, well, that's specific coordinates. I'm free to choose any coordinates around P. So can I choose the coordinates in which the metric will be completely smooth in the whole, in the whole neighborhood of the point P?
These are those coordinates.
Yes, these are specific coordinates. They're specific. They are degenerate at the horizon, right? These coordinates are not good at the horizon, right? So my question is whether your metric is regular at point P in the usual sense.
Yeah. I'm saying no, it's not. I'm saying that this exactly. You cannot find smooth coordinates where
if it's not regular, then its curvature at P is not defined.
Yes, that's true too. That's true too. So the curvature is 0 every. Yeah.
That's what I'm saying. That at the point P, at every point P at your horizon, the curvature is not defined. In my sense, it's distributionally infinite. There.
It's not distributionally infinite, I wouldn't say, but it's 0 everywhere. But then it becomes not confined. It becomes not defined at the horizon. I agree.
All right, not defined. So that's kind of singularity then. Yeah.
Exactly. I completely agree with you. That's what I'm trying to say. It's a different singularity than a curvature singularity. I don't think the right way to say it is that. I mean, it's let's put it this way.
Yeah, it's a curvature singularity. Yeah, it's a curvature singularity. It's like conical singularity. You see, in the usual cone.
It's exactly. It's more like a conical singularity. Yeah. Exactly. It's like a conical singularity. It's not a curvature singularity where the curvature is blowing up and then it reaches infinity as you get to it. It's 0 everywhere.
It's not.
It's like a conical singularity.
Yeah. But some people say that the cone.
It is a conical singularity. It's not just it's a conical singularity. Exactly. That's exactly right.
Then we agree. Then we completely agree.
Yes.
So this is still kind of singularity because no observer can cross the surface, etc.
Exactly.
So it has to annihilate with its outer ego on the other side, etc.
Exactly.
And now this singularity, let's call it conical. It doesn't matter. A cone is you can say that a cone has an infinite curvature at its top, delta functional curvature. Some people can say that, but it doesn't Yes. Now this singularity has to be supported by something, by some kind of matter singularity. Then maybe it's your radiation that goes along this horizon. Radiation from annihilation that goes along the horizon that supports the singularity. Can you think it's in this term?
So I don't think so. So in other words, I think the situation is a bit different than that. That if you took a one-sided cone, then the way to think about that is to think that what is supporting the curvature in that at the point of the one-sided cone is some matter living at the tip. But that when you have the two-sided cone joining, that I think it depends on how the two sides are joined. And because what can happen, one of the things that we show in our appendix is that if you look at the if you calculate the total charge or the total mass or the total angular momentum integrating over the two exteriors, you get 0. Because of the way CPT changes the orientation between the two, because the way the identification takes place between the two exteriors, because of the way that you are identifying a point up here as having with a point down here, so you're identifying the identification is changing the normal time orientation, but also you're identifying each point on the two-sphere at the horizon here with its antipodal point over here. So it's also reversing the orientation on the two spheres. When you take both those effects into account, you have this property that the charges, everything, the total Gauss's law over the total two exteriors is 0, just like in the Einstein-Rosen bridge, the total mass or the total charge measured by Gauss's law over the two exteriors is 0. But just like in the Einstein-Rosen bridge, there's nothing at the mouth of the bridge causing that singularity. So analogously here, we think that depending on how the identification takes place, you either can end up concluding from Gauss's law that there is basically a mass of 2m located at the horizon, or a mass of 0 located at the horizon, more like you would in the Einstein-Rosen bridge. But I completely agree with you. There is definitely a singularity at the horizon in this case. It's a different kind of singularity, more like a conical singularity. And the point is just that's it might be we're not saying that there's a problem-free solution. It's just pointing out that there's this other solution.
Yeah.
Which has different kinds of problems. We think they're milder problems, and they get rid of some of the traditional puzzles of the traditional solution. But it's it's very good that you're emphasizing that it's definitely not a singularity-free solution.
Thank you.
Could I just make a little comment?
Yeah, please go ahead. Yeah, please.
It's not the same as having a singular matter source. You'll remember that in the Euclidean picture of the black hole, there's nothing there at r equals 0. The Euclidean metric is completely regular and solves the Einstein equations and is the saddle point of the action. Actually, what's more important than solving the Einstein equation is that this is really a saddle point of the action. And in the action, the square root of g appears along with the Ricci scalar. And it's that combination that ends up making the saddle point equations completely regular at sigma equals 0. There is nothing on the horizon. There's no need to put any matter on the horizon.
Yeah, Neil, I wouldn't agree that Euclidean metric is regular. It is singular. There is a conical singularity, unless you have
there is no conical singularity. You remember in the Euclidean picture of the black hole, the choice for period of imaginary time.
Oh, exactly.
The choice. So our solution is simply the analytic continuation of that solution. So if there's nothing,
sure, but I agree. Yeah.
If there's nothing in that picture,
but if you don't make this choice, this periodic choice, then it's singular there, right?
No, we're solving the Lorentzian equations.
There is a conical. No, what I meant was a simple thing. You of course know very well that a string, an infinitely thin string in cosmology, creates a conical singularity.
Yes.
Right?
We don't have that here.
Yes, but maybe, so I thought maybe a radiation that's traveling along the horizon, which should infinitely dense.
Exactly. No, not infinitely dense.
Corresponds to that singularity.
No, in the stationary black holes, there is nothing on the horizon. In a dynamical black hole, there almost certainly is something on the horizon. But we haven't solved those equations, so we haven't seen that yet.
Neil, could we ask, if you have a collapsing star, is it physically admissible to have a conical singularity forming and then continue through that? Or?
We have not studied the dynamical solution. Okay. The only way to study it would be to impose the boundary conditions Latham was describing. Namely, you've got to in effect post-select at scry plus infinity, scry plus, as well as scry minus. So you're looking for a saddle point to an action principle with boundary conditions defined at plus infinity and minus infinity. And that, it's not a Cauchy problem. Okay. It's a shooting problem. So in effect, you would have to adjust the boundary condition along the horizon to ensure that you hit the right solution going out. So it's more difficult than standard numerical GR. It's a shooting problem.
Even the Oppenheimer-Snyder solution will become non-trivial, is it?
Yes, exactly. Yeah, it will become a shooting problem, not just a time evolution problem. Yeah. But it may be perfectly doable, but it is inherently non-local in time.
Yuri, something more?
No, thank you very much.
Thanks, Neil, for the clarification. Yes, indeed. Sorry, indeed. You're quite right. You're quite right. If you choose the right period, then at least in the stationary case, there's no conic singularity.
Thank you all for a nice discussion. So we go on. Bernd, please go ahead.
Sorry for the delay. My computer. I have a question concerning dynamics. You still have a kind of a degenerate metric, and normally this can also give an endpoint to geodesics or other timelines or something like this. So can you avoid this? That would be my question. Can you avoid timelines or world lines ending at your degenerate points or?
Yeah, that's another way to see that there is something singular going on. Is that if you, I mean, if you want a geodesic to continue in the forward time direction, then its only option is to head up the horizon. So it seems like, what one picture is that. Sorry, I'm trying to avoid the sun behind me to make myself visible, but so I guess there is a perspective where you think of the two annihilating particles as forming together to form a single trajectory that turns backward in time. That's kind of a Stuckelberg type reinterpretation of what the black hole is, of what the antiparticle is. But if you want to think about forward in time geodesics, then it seems like you're stuck, that the singularity shows itself there, that you end up hitting the horizon and then moving up it.
You're right.
If you look at
continue. I was imprecise.
Sorry.
You can also have closed time-like curves. Then yes, it doesn't have to be it.
Maybe not closed, but curves that turn around in time.
Okay. Okay, time would be the next question, because you use Wick rotation. How do you get back from, or is it just a mathematical procedure how do you get back from a 4-dimensional space-time to a 3+1, 4-dimensional space, sorry, for 4-dimensional space to a space-time?
I was just using the Wick rotation as a motivation because in that context, I find it geometrically easier to see that that there one can analytically extend to get the double sheeted space-time with no interior. But then we Wick rotate back to Lorentzian time. So another way would be to just work purely in Lorentzian time and just say,
okay,
if you basically if you just take the Einstein-Rosen extension to the two exterior regions, and then you switch to Eddington-Finkelstein time coordinate, and then demand that it uniquely covers.
Okay, it was just to ease calculations that has no physical perspective.
Yeah. Yes,
okay.
yes, and it is relevant to this question that Yuri and Neil were just discussing about whether it brings in that there is that exactly in what sense the horizon is singular or not is connected to this Euclidean analysis.
Okay, thank you very much, and good luck with the sun.
Thank you. Thank you. Janik, please go ahead.
Do you hear me?
Yes.
Okay. Did I get it right that one of the interpretations is that this mirror universe is just a CPT-symmetric copy of our universe?
I don't feel sure of that, but that is one possibility, yes.
Okay, so the question is, does it mean that in this mirror universe time is going backwards?
On both sides, well, you always have to be careful what exactly you mean by time in general relativity, but sorry, let me, my computer is running out of batteries. So you can choose a global time coordinate that runs forward throughout, that globally covers the space-time and runs from, so in the picture, sorry, try to block the sun so you can see my hands here. So if you draw the two sheets of space-time like this, joining at the bottom, which is the Big Bang, then you can choose, the conformal time coordinate runs down one sheet to 0 at the bang and then up the other sheet. So it just continues from -infinity to +infinity. But if you want to take but the actual direction of the thermodynamic arrow of time is that it points away from the bang in both directions, or in other words, entropy is increasing as you go away from the bang in both directions. So you can also choose a time coordinate like that, but then it's not, a time coordinate like that is not single valued on the space-time.
Okay, so it's folded, I would say.
It's what? Yeah, folded, yeah.
Folded, yeah. And when we unfold it, it means time goes backwards, but when it's folded, it's just going forwards in both universes.
Yes, exactly.
Okay, thank you.
Yeah. Latham, there's a comment from Tavian. I'll just read it out. Tavian writes, I believe that Isaac Asimov wrote an essay in which he postulated multiple copies of the universe with opposite orientations, negative mass, etc., so that all total measures, for example, the mass of the universe, would always be 0.
Oh, that's interesting. You know, there was also an interesting paper a couple of papers in the 70s by I'm blanking on his name. Sorry.
Edward Tyron? Tyron? Tyron?
No, I was sorry. I was thinking of Andrei Sakharov. Also thought about a cosmological model where there's sort of cancellation between everything between the two halves of the universe.
Yeah, thank you. Hillary, please go ahead.
Hi there.
Hi, Hillary.
Hi, everybody. This is perhaps a slightly, I don't know, very, I'm not going to say very physicsy, but listening to your talk, Latham, what you describe with this reflection where you have a particle coming in and then an antiparticle coming out, apparently, and it's not clear what universe it's in or what have you, whether it's going forwards or backwards in time and da-da-da-da. What that reminds me of is something called Andreev reflection with superconductors. So you have a particle coming in with an energy less than the superconducting gap, right, into the surface of a superconductor, and that forms a Cooper pair. And in order to conserve lepton number, then you have a hole coming back. Right? And so on the other side of the horizon or interface or whatever you want to call it, what you've got is a pair of particles in a superconducting state.
Well, I don't. I've heard the term. I think I need to look at it in more detail, but that sounds interesting. Thank you.
Yeah, I mean, everybody seems to be floating different ways of matching the boundary conditions and different ways of interpreting it and all the rest of it. So I thought I'd chuck that one in there as maybe another alternative. But I mean, Andreev reflection is a quantum effect, and we're supposed to be doing general relativity here. So, you know, does general relativity need an analog of Andreev reflection in order to make the solutions work? I don't know.
Yeah, I mean, so one of the interpretations that Neil and I gave for this whole CPT-symmetric universe idea was that because you can just like Stuckelberg had this interpretation where antiparticles were, you know, so Stuckelberg's interpretation was that you have the time in the embedding space-time, but then you have the proper time running along the world line. So there's the sort of, if you try to embed a world line in space-time, there's the intrinsic time along the world line, and then there's the time in the embedding space-time. And, you know, the difference between a particle and an antiparticle is basically whether those two times are aligned or anti-aligned. Analogously, you can think of the embedding of space-time in superspace in the sense of not supersymmetry, but in the sense of the way quantum gravity folks think about superspace, like in the sense of the space of all metrics. And in that sense, you can think of that also has a time-like, superspace has a time-like direction. You can ask about whether the time direction intrinsic to your 4D space-time is aligned or anti-aligned with the time-like direction in superspace. And these CPT-symmetric universes do have this property, you know, just like Stuckelberg's took a world line like this, and where the proper time turns around relative to the embedding time and reinterpreted that as a particle-antiparticle pair appearing out of the vacuum. You can reinterpret these universes where the scale factor decreases and then re-increases analogously as saying that the time direction intrinsic to the 4D space-time is turning around relative to the time in the embedding space-time, and it looks like a universe-anti-universe pair being created out of the vacuum. So yeah, it's very plausible that there is that there's some. It seems very likely that the question of why there is a bang with this strange property is to interpret it properly in one way or another involves relating GR to quantum mechanics. We have this particular proposal about defining the wave function of the universe, but maybe there's other ways to do it. But anyway, one way or another, I think probably GR and quantum mechanics have to interact to explain it. And it sounds plausible to me that it's. I have to look into it, but it sounds not implausible to me that it's related to this Andreev reflection story. So that's interesting. Thank you.
Thanks.
Thank you. Latham, so Neil, you know, a few months back when your paper appeared on the archive, I told myself this is going to cause a stir and lead to a lot of discussion. So I'm curious, what kind of did you have feedback apart from the kind of discussions we had today?
I'm going to close the shade. 1 second. That's my new solution for.
Did you have? Yeah, please
let's
go
see.
ahead.
Yeah, you know, it seems like a lot of people are interested, and yeah, I think we've gotten more questions than, but questions along the lines that we've had today. I'm trying to think. Neil, are you still here? Do you have any particular thoughts about this or anything that comes to mind?
Yeah, just one comment that when I visited Cambridge, which of course has always been a center for GR for a long time, and discussed with people there, Malcolm Perry and Gary Gibbons, they were both very interested in this, and yeah, gave quite useful feedback. In fact, Gary referenced us to some articles on how to represent black holes as algebraic varieties in higher dimensions, in higher flat dimensions. And yeah, he thought they might be very useful. There are some under-referenced papers which show that you can write the Schwarzschild black hole as an algebraic variety. And because we have a certain kind of singularity, which looks like it could be resolved by embedding the space-time in a high-dimensional flat space, and then what's called blowing up, which is basically replacing a curve which, let's say, crosses itself by just lifting the crossing point in an extra dimension, and then everything becomes non-singular.
What would be the dimensionality of the higher dimensional space?
Yeah, it's not that space-time is high dimensional, it's just that the embedding space is high dimensional. So
yes.
If you have a loop if you draw on a piece of paper a curve which crosses itself, that curve is singular at the crossing point because the dimensionality
so
is not clear.
You wouldn't think of the embedding space as having a physical reality.
Not at all. It's merely a mathematical device. And this is there's a theorem by Hironaka that says you can always resolve singularities in the systematic procedure, which ends up being coordinate invariant. So yeah, so we're thinking about this, and first of all using it in cosmology, but secondly for black holes. It may give completely unambiguous answers.
But Tejinder, you'll be glad to hear that in the cosmology case, there's the embedding space has one time dimension and 8 space dimensions. So
very interesting. 8 plus 1.
Anyway, Neil reminded me of one other thing that might be of interest that I meant to mention about the reaction in Cambridge, which is that Stephen Hawking in 2015 or something wrote a very short telegraphic paper basically pointing out that well, as I say, it's very short, but it's called, I think, Black Holes and Weather Prediction, and but one of the points he makes there is that there's a way that it seems like a problem, and that he's trying to propose a solution for there, that the usual black hole solution doesn't settle down to a CPT-symmetric state. I mean, there's sort of quite general arguments that when you have a system that settles down to thermal equilibrium, that it should also settle down to a CPT-symmetric state, and yet that's not really what a black hole does. You form the black hole, you let it sit there, it settles, it rings down to a stationary black hole, and yet it's still in the normal picture completely not CPT symmetric. There's no way for time symmetry to act on it. It has a black hole horizon, but no white hole horizon, etc. So that's another motivation that we think of for this picture is that it is an alternative picture that does have this expected property that when you settle down to thermality, you're also settling down to a CPT symmetric state.
This also just reminded me, I think Quanta had an article on your work on the CPT-symmetric universe, maybe a few months back. You were quoted as mentioning something, I think, called super octonions.
Yes, that's something where, yeah.
Can you say something about that? I remember, I wanted to ask you, is this Grassmann number valued octonions, or is it something else?
Yeah, yes, it's letting the parameters you can consider the complex numbers, you can consider the division algebras over the real numbers, over the complex numbers, over various different fields. But then you can also ask about algebras over superfields in the sense of DeWitt. And so the paper isn't out yet, but my student Vatsalya Vaibhav and I have done a classification of algebras over those fields. And one of the
did this come up in the context of the CPT-symmetric universe or something different?
No, we were thinking about that in the context of trying to explain the standard model. Now, I must say that I sort of think and hope all these things are ultimately connected to one another, but it was about trying to.
Yeah, I came across something like that in the context of square root of the Dirac equation, where instead of writing the Dirac equation over space-time vector space, you are writing it over a square root of space-time, which would lead to something like Grassmann number valued octonions or octonions over quaternions over superfields. Yeah.
Maybe you could send me the reference. Yeah, it sounds interesting.
Nothing written up.
Oh,
yeah.
I see. You've been thinking about it, you mean?
Yeah. Then
it sounds interesting.
Before I hand over to Cole, just a side question. You've seen these papers by Tooft saying there's a factor 2 off in Hawking's temperature calculation. Did that type anywhere with your CPT symmetric solution? No.
Yes, as a matter of fact, yes. So we find something similar in the let me remind myself exactly what the story is here. So for example, we had a paper a few years ago where so Neil and I found the exact solution of the Friedmann equation for a kind of realistic universe that just has the components we think have to be there: radiation, matter, vacuum energy, and in principle you can let the spatial curvature be there as well. So the general solution of that is a very nice complex analytic function, meromorphic function. It's this elliptic function. It's a rational function of Jacobi elliptic functions. And so an interesting thing that happens there is that when you have these elliptic functions, they can be periodic. They can have different types of periods, and there's two types of imaginary periods that this elliptic function has. One is, if you think about the function as an elliptic function is a complex function that really can be thought of as living on a torus, a Riemann surface, which has the topology of a torus. So one period you can calculate is the period as you go around in the imaginary time direction around the torus. Then there's another thing, which is that the function has poles corresponding to the de Sitter when the scale factor expands to infinity at the de Sitter boundary of the space-time. And you can calculate the imaginary period in time as you go around the pole. And that period gives the usual de Sitter value, but as you go around, as you calculate the temperature in the other imaginary period, it's at least in the case of when there's no non-relativistic matter in the space-time, it's exactly half. It gives you exactly half the temperature, just like the Tooft claims for the black hole. Yes, so we do encounter something similar.
That's very interesting because you have something like a boost for your proposal. I don't know where Tooft gets.
Yeah. I mean that's another good point. Is that Tooft also has clearly been thinking about ideas that in fact, now that I mention it, there's a number of various interesting things in the literature that clearly rhyme with what we're talking about here. One is the stuff that Tooft has been doing. Gary Gibbons wrote a very interesting paper about looking at the so-called elliptic black hole, which is where you don't just identify at the horizon, you identify all CPT conjugate points throughout the black hole, which leads to it doesn't lead to the black mirror. You still have interiors and exteriors, but instead of having two interiors, you have one, and instead of having two exteriors, you have one. And there's also an interesting paper by Nyash and his F. Shorty at Perimeter and his student, former student, I'm blanking on his name at the moment, but they had a kind of interesting paper where you glue two exteriors together, not at the horizon, but at some exterior radius outside the horizon. So it's a time-like surface instead of a null surface. But anyway, so just thanks for reminding me. There's a few other interesting relevant papers here that we give a more complete list in the reference section.
Thank you. Cole, please go ahead.
There you go. Can you hear me?
Hi, Cole.
Yes.
Hi. Great talk, Latham. I was just curious about the superoctonions. Can you explain? Is it like octonions with, for example, like real coefficients and or where you take the coefficients and you replace them with Grassmann variables? Is that the idea, or?
Yeah, there's a nice book that I recommend called Supermanifolds by Bryce DeWitt.
Okay.
Where he discusses these the field of supernumbers, which are a kind of superfield extension of the real or complex. You can have the real supernumbers, the complex supernumbers. Indeed, where there's a kind of the so-called you can divide any supernumber into its body and soul, where the body is the kind of ordinary number part and the soul is the Grassmann part.
Yeah.
So the real supernumbers, for example, the body of the real supernumbers would be the real numbers.
Yeah.
But anyway, they're a kind of super extension of fields, and you can just like you can think about norm division algebras or composition algebras, classify them over various different ordinary fields. You can think about classifying them over different superfields. And so you then get algebras where the body of the algebra would be let's say the real octonions, but the full algebra would have also a Grassmann part. It's interesting because, for example, like I'm interested in, in this magic square construction of Lie algebras. There is this, when you express it in terms of triality, it has this nice property that any of the magic square Lie algebras naturally decomposes into a super algebra in the sort of sense of being Z2 graded, that there's a bosonic part that comes from, there's this way of expressing any algebra in the magic square as triality of the first division algebra plus triality of the second division algebra. Let's say you call the two division algebras K and K prime, then it's plus 3 copies of K tensor K prime, exactly.
Yes.
And if you take the two triality algebras and one of the copies of K tensor K prime, that's always the bosonic part.
Sorry, can you say that again? Which is the bosonic part?
If you take triality of K plus triality of K prime plus 1 copy of K tensor K prime, that is always the bosonic part.
I see. Yeah.
And then the other 2 copies are the fermionic part. And you can choose that split in any of the 3 ways you want.
Yeah.
And in particular, for the largest of those algebras, E8, the bosonic part is SO10, and the fermionic part is the spinor, the 16-dimensional spinor of SO10. So it's intriguing. Now, when you can repeat, this whole story now has a super extension in terms of these superoctonions. But then the intriguing thing is that the bosonic part is really bosonic. It's really over the real numbers, whereas the fermionic part is really Grassmannian. It genuinely behaves as a spinor over Grassmann fields. And so there's various interesting things that change a bit when you think about these algebras over the superfields, which seems to me to rhyme a bit better with physics.
Yeah, fair enough.
Right.
Yeah, thanks.
Yeah.
Look forward to your paper. So you are saying if we, let's say, address the standard model with the super octonions and not just the real octonions, we learn something more?
Yes, although we're also still even just super confused. We were previously confused, and now we're yeah, super confused.
Yeah, somehow I think there is something to the square root of the Dirac equation, where on the right-hand side you have square root of mass with 2 signs instead of mass, and on the left-hand side you use a super quaternion.
Okay, sounds interesting.
Yeah. Latham, could you kindly stop sharing so that we can see each other and say bye?
Oh, yes.
Yeah, great. So, Michael, are you there?
Yes, I certainly am, and that was a fascinating talk. Thank you very much indeed, Latham. Can I ask
thank
one
you.
very quick supplementary question about the superoctonions,
Mm-hmm.
and particularly the Grassmann part, and in the connection with the superfields? Has this got? Is there any connection here with the Sedenions, the 16-dimensional division algebra?
Not really. Not as far as I can tell. I mean, they have. Not really. I mean, there's a sense in which they're both different doublings of the octonions, but they're really two different doublings.
Probably,
You know,
Michael, we could have super Sedenions. Yeah.
Well, yes, of course, you know, that's the
Yeah.
thing. Once one gets started on this ladder, going up, but it just seems that okay.
In particular,
they are indeed, as you say, both essentially doublings of the octonions, and they both, as I understand it, do involve bringing in essentially the Grassmannian part and the other part of the quantity, which I just it was just I was hearing about this for the first time, and I wondered if there was a connection. But
I don't. I think they're basically different. In particular, the superoctonions are supercomposition algebras in the sense that they still or you can think of them as super norm division algebras. Whereas the Sedonians are not. So there's a sense.
No, they're not associative either. This of course makes sense.
Neither of them are associative. Yeah.
Yes.
If I square,
in fact, that's true. Neither is associative.
You go ahead. If I square a superoctonion, I would get a body and a soul, or only the body?
A body and a soul, yeah.
Okay. Mm-hmm.
You'll get a super number.
Okay.
Mm-hmm.
These, of course, are terms of art coined by De Witt.
Yes, but in other words, I think that Tejinder was wondering, if you take the norm of a superoctonion, will you get back to an ordinary number? And the answer is no. You'll get back to you'll get a super number. If you want it to be a norm super division algebra, then the norm needs to be defined in this way, where you get super number in.
Very interesting. I do have that book on supermanifolds of De Witt on my shelf, but I'm ashamed to say that I have never read it right the way through. I mean, I have opened it. I have actually read 2 or 3 chapters of it, but I was never able to quite nerve myself to try to tackle the whole thing. But I should try and do so again. It's obvious.
Well, it's like all of the De Witt, anything De Witt writes. It's very clear and a little bit long.
Well, yeah, it's great. Yes, he was certainly a great mind. I'm glad to say we have quite a lot of recordings of him in our archive. Actually, to publish one day. Okay. Well, thank you again, Latham. That was
thanks again, Latham, for a great talk.
Yeah. All right. Thank you for the invitation, and thanks everyone for listening. Nice to see you all.
We meet 2 weeks from now. Indranil Banik will talk on the Hubble tension in cosmology. So look forward to that very much. Yes.
Yes. And it's very good to have this alternation between what you might call more sort of, purely mathematical extensions of the formalism-oriented talks and ones which are more focused on specific topics in cosmology. I think it's providing a very good kind of yoga.
Great. So, bye, everybody.
Okay, see you all in 2 weeks. Thanks to everyone.